All right, in this lesson, we're going to review a lot of topics from Algebra 1, so hang on for the ride. Hopefully it begins pretty easy and may challenge you towards the end. We'll see. Now, we're just talking about relations and functions. There's 4 ways you learn to relate a function or a relation. One way is to graph it. All right, we can graph it by putting all the points there, right? Another way is to put them in ordered pairs. Remember x and y. X is always the input, y is always the output. By the way, these points are the same points on this graph over here, so they correspond. Another way we could represent a function or a relation is in a table. These points are the same as the ones in the table, okay? Input, output, input, output. The 4th way is just a mapping diagram. Now, I'm just going to use these same points and map them. When we do it, we do least to greatest in your x column, least to greatest in the y column. So looking at my input, they're least to greatest already. So I'm just going to do -5, -3, -2, 0, 2, 4, and 5. My output, however, is not least to greatest, so I have to stop and think, and we'll put them in that order. So it'll be -5, -2, 0, 2, 0, 1, 2, 6, it looks like. 1, 2, and 6. Now, to map them, I just draw arrows. So 5 goes to 1, -5 goes to +1, -3 goes to -2, -2 goes to -5, 0 to 0, 2 to 2, 4 to 6, and 5 to -2. All right, all ways we can relate a function. Now, the question is, next, what is the domain? Well, domain, remember, are the x values. So we would write it like this, with the curly bracket, least to greatest, so -5, -3, -2, 0, 2, 4, and 5. All unique numbers listed from least to greatest. The range, same idea. Curly brackets, least to greatest. So we go -5, -2, 0, 1, 2, 6. All right? Is this a function? Well, how do you know? Well, you can look at the x values here, and they're all unique. Now we look here and make sure we don't repeat the same x values somewhere, and we don't. So all my x values are unique. Nothing gets repeated, nothing gets used twice. Although some of them point to the same y value, that's okay. We can repeat y's, we just can't repeat x's. So is this a function? And we would say yes. Why is it a function? Each input is unique. Or you can say no repeated x values. That's how we know it's a function. Now remember this, domain is the set of all x values, or the input, maybe you were taught input values, in a relation. The range is a set of all the y values, or the output. Okay, all input, all output, okay? Now, the function is a relation that has only one input for every output. In other words, no repeated x values. Now, looking at these examples, let's see what we got. It says list the domain, the range, and determine if the relation is a function. Okay, so look at number 1, it's a mapping. My domain is my x's, so I would write this. Domain is least to greatest, so -3, -2, 0, 5, and 7. My range, least to greatest again, -4, 1, 0, 1, 3. All right, now to determine if this is a function, I'm just going to make sure that no one of these inputs is used twice. Each one is unique. Each one's unique, so this one is indeed a function. So this is a function. We're good. Now let's look at number 2. This is another way you could look at a function, is a list of ordered pairs. So first let's do domain, okay? Now domain has to go least to greatest, so let's scan this for our lowest number for x. That would be a -4, then -2, 0, then we have 2 1s, notice that. We have 2 1s, and then we have a 2. All right, now the range, again, least to greatest, so look at your lowest y value. Is that 3? So 3, 5, 6, 8, then 9. Now, is it a function? Well, the fact that we had two x values that were positive 1 means that we have repeated x values. So this is not a function. All right, now graphically, look at this. We're going to do domain and range here, so I'm going to zoom in a little bit. So if I domain this, let's go left to right, least to greatest, so that's what, -3, then -2, then 0, 2, 4, and 9. Range, my y values, so I start from bottom to top, so I'll go 5, 6, this is -6, then -5, working my way up, 0, 2, 3, 4, 5, and then 6. Okay, now, let's see if any of these x values repeat. Well, graphically, it's not so hard because you can look at this and see this x value is used twice. So since that's true, this is not a function. All right, and it brings up the next part on the next page. So let's switch pages. You can use the vertical line test. It's the test that states that if the vertical line passes through one or more than one point on the graph of a relation, then the relation is not a function. That's what we visibly saw on that last graph, okay? So these are really quick. Use the vertical line test to determine if it's a function. So all you have to do is draw a straight vertical line through it. If it only hits once, then it's a function. So this is clearly a function, only one intersection. This one, if I do a vertical line, it hits twice. So this one's not a function. Number 3, vertical line only hits once, so this one is a function. Easy peasy, got that down. Now, let's move on to the next topic. Maybe you want to pause, get a cup of coffee, whatever. We got a page and a half to go, so hang on for the ride. Now, in this section, we're going to talk domain and range. We're going to talk set builder and interval notations from Algebra 2. Let's see what you remember. So let's say I had a graph that looks like this, -3, and it's shaded to the left. So if I needed to write in, I'm going to put set on the left, and I'm going to do interval notation on the right, okay? So if I do set builder for domain, looks like this, x such that, now notice there's x, and it gets smaller, so it's less than -3. Now I use less than, I don't use less than or equals to because it's an open circle. Now, to put this in interval notation, I read from left to right. Now this is like going to negative infinity, right? So it's negative infinity to -3 with a parenthesis. Now a couple rules of this. With infinities, you always put a negative because it's not an exact location. Over here, I could put a bracket or a parenthesis, but since it's an open circle, it never really equals -3. It just approaches it. So we put in a soft bracket. We don't put a hard or a parenthesis. The bracket means it includes the -3. Not the case in this one. Let's try another one. What if it looked like this? -3 to 4. All right. This one, my domain would look like this. X is between these values, right? From -3 to 4. So I'm going to put it between two inequalities. So -3, x, and then less than 4. Now my inequalities will always go this direction. They'll always be less thans when it's a between question. So then I have to just decide, is it an or equals to or just regular? Since this one is closed over here on the left, I have to put the or equals. Okay? Now, to put this in interval notation, I'm going to use left to right. I'm going to go -3 to 4. Now let's stop and think. It's not a parenthesis here. It's going to be a bracket because it's a closed circle. So there's a bracket, but on the 4, since it's an open circle, it would be a parenthesis. Let's try one more. Let's say it goes from +1 to the right, okay? So this domain would be x is getting larger, right? Is greater than or equal to a -1. So my domain statement in interval notation would then say from the least it gets is -1 and it goes to a positive infinity. And I would have put a closed bracket on it because it is equal to -1. We're going to practice this some more on some other graphs, so don't panic if you're still unsure. That's your first exposure to it. Now, let's look at these graphs. Find the domain and the range of each function in set builder and interval notation, then determine if it's a function. All right, so here we go. I'm going to zoom in here. Now, domain and range. I don't know what your background was like in Algebra 2, if you got this or not, but I'm going to do my best to help you out. Domain is your x values, right? So to get domain, you want to basically collapse this down to where it hits the x-axis, all right? And notice there's an open circle here and a closed circle here. That's important for us to decide on our endings, okay? Now in set notation, my domain is going to go from, let's see, it's the curly bracket, so x, and it's a between, right? X is between these, so it's going to be -2 less than x is less than, what, +3? Now, this one's closed up here, so it has to be or equals to. The -2 is open, so it is left that way. So in interval notation, that's going to be a parenthesis, -2, comma, 3 with a bracket. Now for range, we're going to collapse down to the y-axis. So we're going to go this way. What y values will it be using? Now it stops right there, doesn't it? It stops right there. So only those y values are being used. So that's what my range will reflect. So from bottom to top, y such that, where is it? 1, 2, 3, 4, 5. So -5 to 5. Now, this one is or equals to, the other one is not, so the endings will look the same, but the numbers changed. Let's look at number 2. All right, domain. My domain, if I collapse it down to the y-axis, look, it's going to go this way all the way over, right? So my set notation domain would look like this. It's going to be x such that, what is this? 1, 2, 3, -4. X is greater than or equal to -4 because it stops at -4 and it gets larger and larger. So left to right, over here, I'm going to put a hard bracket on -4 to positive infinity. Now let's switch gears and do range. My range, the lowest it gets is right there, and it goes up forever. Now that indicates it's going on forever, never, never, never. So let's make sure our notation looks like that. So this will be y such that y is greater than or equal to 0. It never goes negative, so it's greater than or equal to 0. So from bottom to top, I go from 0 to positive infinity. We put a hard bracket on it because it does include 0, but we put the parenthesis on infinity because it's not a real location. Let's try one more. Maybe you want to pause the video and try it yourself and then check yourself, okay? Maybe so, who knows? So let's look at this. Let's see what our domain would be in this case. So again, collapse it down to the y-axis. Now remember, it looks like it stops right here, but look, that arrow means it's going on. It's going to cover all these x's if we collapse it down, if we zoomed out. It's going to cover everything. So when I write my notation, it's going to include an infinity going to the negative side. So x such that x is over here and it's getting lower, right? So 1, 2, 3, 4. X is less than or equal to a 4, all right? And then my interval notation, it's going to start at negative infinity because we always go left to right, by the way. Negative infinity to 4 with the hard bracket. Now, with range, okay, the highest, that arrow means it's going on forever, never, never. So if we go from bottom to top, it's going to stop right here where x is 1, 2, 3, 4. So we indicate that in our notation. Bottom to top, so y such that y is less than or equal to a positive 4. And then in interval notation, that would be from negative infinity to 4. They look the same, don't they? All right, hope that's beginning to make a little more sense. Let's try our last page. A couple more. All right, domain. Look, what x values would be covered? Okay, there are 2 arrows here. That means everything's getting covered. So my domain notation would look like this. X, curly bracket, x such that x is an element of all real numbers. So just two vertical lines and make it an R. Interval notation, that would be negative infinity to positive infinity. Now the range, let's look at our y values. What's happening here with our y values? From bottom to top, it starts from here and it goes up forever and ever and ever. So set notation would say y such that y is, it's getting larger, greater than or equal to a negative 1. And it does include the negative 1 because this like a closed dot right there. So this would go from negative 1 to infinity. It does include negative 1, so it gets the hard bracket and a parenthesis on this one. Now, number 5. Let's look at this. Domain, if I collapsed down, where would my domain be? Well, starting here, it would go all the way out, right? So that would be x such that x is greater than or equal to 0. So in interval notation, it would be a bracket, 0 to positive infinity. Now range, these little arrows mean they're going on forever and ever, right? You could extend those. So my range would be y such that y is an element of all real numbers. So that means it goes on forever. Interval notation would say negative infinity to positive infinity. Okay, that's domain and range. Now let's look at how do you find domain of a function if you don't have a graph? Now, this is a good place to pause and come back later because there's a little bit more to cover here, and I don't know what you've seen before, so it may be new to you, all right? But if you take a break, come back, here we go. So finding the domain of a function, here's a couple things you need to do or need to know when it comes to finding the domain of the function. The default domain of a function is all real numbers, okay? All real numbers. It wants to go on forever and ever and ever and ever. That would mean like your graph just wants to keep on going. No interruptions at all, okay? That's fine and dandy as long as every x value can give you a y value, right? However, there are limitations to some graphs, and we're going to show you some. Couple things that can happen. It can become imaginary, it can become undefined, and we want to avoid those places because that's where x doesn't exist. So look at these equations. I'm going to show you some tricks, okay? Look at this one. H of x equals x squared plus 5x minus 7. Now, maybe you remember this, maybe you don't. Maybe you remember that this is a parabola because it's x squared. That looks like that, right? It's a continuous curve. It goes on forever. So my domain would then just be negative infinity to positive infinity. That's it. It's the default, okay? The default applies to this one. No craziness. Now, B is one scenario where you can't say all real numbers, and that's because this is the square root graph. If you remember, you can't take the square root of a negative number. So we have a limitation. We need this 4 minus x to stay greater than or equal to 0. It can't be anything less than 0. So we have to solve this to find out where is it greater than or equal to 0. So maybe you remember when you solve a square root, you're going to take this, you're going to square both sides. When I do that, I have 4 minus x is greater than or equal to 0. I'm going to keep my x on the left side, by the way. If I move my 4 over, that's fine. But now when I divide by the negative, you remember when you divide by negative, it flips the inequality. So this is less than or equal to a positive 4. So x has to be less than or equal to positive 4. So let's think about this. Visualize this on a number line. It really helps. If this is 4, can it equal 4? Yeah, 4 minus 4 is 0. That's legal. We can do that. It's not negative. But it has to be less than. So then when I do my notation, read it from left to right. That's going to negative infinity. So it's negative infinity to 4, but then it stops. That is the limitation on it. So anytime you see a square root, you have to do that. What if it is something like this? This is a rational function. Now, the problem with rational functions is that you can't divide by 0, right? You can't have this guy be undefined. You can't end up with a 0 on the bottom. That can't happen. That is undefined. That's a no-no. Okay, so that's going to limit our domain. It's going to cause a break in our graph. So if you graph this, you would see that there's an asymptote and there is a break. But you don't want to graph it, so let me show you algebraically how to do this. So we are concerned about the denominator. The numerator doesn't matter. We don't really care. That's not going to be a problem. It's the denominator that could become a problem. And it becomes a problem when it equals 0. So when we do domain, we say it cannot equal 0. And we're going to figure out where does it not equal 0. Well, let's just solve this. So 4x cannot equal 1. So divide by 4. That means x cannot equal 1/4. That's where it breaks up. So then think of your number line. If here's 1/4, it cannot equal that, but it can equal everything else in both directions is fair game. So that's negative infinity. This is positive infinity. So when I write my notation, notice there's two sections here. There's a section here, and there's a section here. So there's going to be two parts of my domain statement. It'll go from negative infinity to 1/4, and then it jumps, and it goes from 1/4 to positive infinity. Now you're like, hold up, you can't be 1/4. You're right. The parenthesis doesn't mean it can equal 1/4. It just gets really close to it, but never actually is equal to it. Now, hopefully this is making a little sense. Now, before we jump on, I want to come over here and do one more example that wasn't written in your notes. Let's see. Let's do example D for a second. Let's say I gave you an equation like this. 1 over x minus 1 over 2x minus 3. What the heck would you do? Well, we know there's going to be limitations to our domain. It's not going to be the default because these are what we call rational expressions. They're fractional and x is in the denominator. If x is in the denominator, then we have to set each one of these denominators not equal to 0. So x cannot equal 0 for this equation, and then 2x minus 3 cannot equal 0 for this part of the equation. And then we just solve it. So this one's done, right? Easy peasy. This one, 2x will equal 3, x will equal 3 halves, or cannot equal 3 halves, I should say. So now, what the heck is going to happen here? Well, visualize this on a number line, draw it out. So it can't equal 0. 3 halves is 1.5, so 1.5. It cannot equal 1.5, or you can write it as 3 halves, whatever. But it can equal anything else. Anything else is good. So again, notice the sectioning, 1, 2, 3. That means your answer is going to have 3 parts to its domain. So I start left to right. I go negative infinity to 0. Then I do the middle section. I go 0 to 3 halves, or 1.5. Then I do the third section on the other side of 3 halves to positive infinity. So 3 sections to my number line, 3 sections to my statement. All right, we'll work some more on this in class. I think this may be a new topic for you, so we'll discuss it more when we get to class. Now lastly, function notation. It just means, f of x just means the same thing as y equals. If we use f of x, it just shows that the equation represents a function. So since the equation y equals 2x plus 3 is a function, we can instead write it as f of x equals 2x plus 3. So to find f of negative 1, we substitute negative 1 into the equation whenever we see an x. So if you ever see the directions evaluate, that means to substitute. Okay, substitute in. So if f of x is x squared plus 4x, and f of negative 3 is what I want, I'm just going to plug in negative 3 where x was and solve it. Negative 3 squared is a positive 9. 4 times negative 3 is negative 12. That gives me a negative 3. That's my answer. G of negative 5. So I'm going to use the G equation. So I'm going to say 5 minus 3 times negative 5. So that's 5 plus 15, which gives me a nice pretty 20. And then lastly, part C, G of negative 2/3. All right, plugging in, that's all I'm doing. So 5 minus 3 times 2/3. Now put that 3 over 1. Hopefully you see the 3's will cancel out, and you just have 5 minus 2, which is a 3. So maybe this is the easiest part. When you're asked to evaluate a function, you're just plugging in and solving. All right, I understand this has been a long video. Thanks for hanging in there, and we will revisit some of this in class. Good luck.